I've been saying that variance in terms of the exact number is a little bit hard to interpret, but now we're going to see a theorem that gives us a little bit of a start towards interpreting it. And it is also quite a useful theorem for understanding and working with expected values and variances. So it is called Chebyshev's inequality. And it will also take some writing down and then unpacking. So let's start by writing it down. Probability of absolute value x minus expected value of x greater than or equal to r is less than or equal to variance of x over r squared. Or an alternative equivalent version using standard deviation instead of variance, probability that absolute value x minus expected value of x greater than or equal to k standard deviations is less than or equal to 1 over k squared. So let's take a minute to unpack these statements. So what is this saying? This part of the equation is, again, very much like we were talking about in the variance. It's measuring the distance between some outcome and the expected or average outcome. And so what is this whole side saying of the inequality? It's looking at all of the outcomes that are a certain distance from the average, from the expected value, the mean. So it's asking, what is the probability that an outcome is a certain distance or more from the mean? And what the whole expression then is saying is that the number of outcomes, or the proportion, the weighted proportion of outcomes that lie far from the mean is relatively small as measured by the variance combined with the distance. Or in this formulation, you can say what proportion of outcomes or what amount of probability lies beyond a certain number of standard deviations from the mean. Again, you can bound it above to say it's fairly small. It's 1 over k squared at most when you're looking k standard deviations from the mean. So this should, this may be familiar if you have heard other rules of thumb, like, being inside one standard deviation or outside one standard deviation, and what that means in terms of how likely it is. This is exactly something along those lines. So let's write down something to that effect. For example, so what happens when we set k equals square root of 2? So we're choosing square root of 2 to make this side 1/2. And then what that's saying is at least 50% of the distribution must lie within root 2 standard deviations of the mean. So what happens if you take k equals 2? Then this becomes 1/4. So it is saying 75% at least must lie within 2 standard deviations of the mean. And if you're familiar with the estimates for the normal distribution, which you don't have to be, but I just want to make the connection because it's very related, this Chebyshev's inequality is not assuming anything about the distribution, so the estimates are a little bit weaker. For a normal distribution, you get, I think even like 95% within 2 standard deviations. Here we're only getting 75%, because we're talking about any distribution at all. So let's see another sort of more concrete example of how we're saying things like this. So let's say we flip a fair coin 100 times. And count the number of heads. Then what's the probability that it's outside the range 41 to 59? So the reason that we are setting this range is because we expect to get about 50 heads. So we're asking, what is the probability that we are far from the average, far from 50, in the sense of being 10 or more away? That's what this question is. And this is exactly the kind of question that we can answer using Chebyshev's inequality. We will just need to know the expectation and the variance and whatever this R or K is that is measuring how wide our range is. So, well, I'll come back to that formula. So expected value, let's think about what this distribution we're dealing with is. We are flipping a fair coin 100 times and counting the number of heads. That's the number of successes in 100 Bernoulli trials with probability 1/2. So this is a binomial distribution. Let me write that down. This is a binomial random variable or distribution with n equals 100 and p equals 1/2. So we have formulas for the expected value and variance of such a thing. The expected value is n times p, which is 50, and the variance is n times p times 1 minus p, which is 25. So applying Chebyshev's inequality, and since we're using expected value and variance, let's use this top version. So the probability of the absolute value of x minus 50 being greater than or equal to 10, because this is, so let's unpack what we're saying here. That is exactly this statement. The probability that x is outside the range 41 to 59 is saying the absolute value of x minus 50 is at least 10. So that is the question that we were asking. And that's exactly what is happening on this side of Chebyshev's inequality. So r is equal to 10. And Chebyshev tells us that this is less than or equal to the variance divided by 10 squared. Let me write it that way. 10 squared, which is 25 over 100. That's 1/4. So the probability of getting a number of heads 40 or less, or 60 or more, is at most 1/4. This is a way of quantifying that it's not very likely to be far from the mean using Chebyshev's inequality. And I want to do a little application real quick to end with. So application of Chebyshev's inequality. So you may be familiar that the mean and the median of a random variable can be different. So I'll recall what the median is in a second. But you may be familiar with the fact that the mean and the median don't have to be the same. They measure similar things, but they don't have to be exactly equal. But you can use Chebyshev's inequality to show that they can differ by no more than √2 standard deviations. So we know that the mean and the median can be different, but Chebyshev's inequality gives us a way to say they can't be just anything. They have to be a little bit close to each other. So let's recall median of a random variable satisfies the probability of being at least that big is at least 1/2, and the probability of being at most that thing is also at least 1/2. So the mean is the sort of weighted average of the outcomes by their probability. The median is another measure of the center of a distribution, but it is slightly different in the sense that it measures the point where half the outcomes lie on one side and half the outcomes lie on the other, without caring how far they are from the median. So the theorem that we're trying to prove is that we want to say that absolute value of mean minus median is less than or equal to 2 sigma of x. And we will prove this. So mu equals the expected value of x is the mean. So we'll prove this by contradiction. So let's say, suppose that m is greater than mu plus 2 sigma. I'm just going to shorten sigma of x to sigma. Oh, I said √2 before. Let's put a root there. Even better. It's within √2 sigma. So suppose m is greater than mu plus √2 sigma. And write m equals mu plus √2 sigma plus epsilon, where epsilon is some, real number bigger than 0, since this is strictly larger. And just as a quick note, we need to also consider the case that m is strictly less than mu minus 2 sigma, √2 sigma, excuse me. But that's the same argument. So we're just going to do this one case. So applying Chebyshev's inequality to this situation, what can we say? So the probability that the absolute value of x minus mu is greater than or equal to √2 sigma plus epsilon. So now we want to use the second version. Oh, it's a long way away. We want to use the second version of Chebyshev's inequality at the top here, which says that being at least k times standard deviation gives us a bound of 1/k². So we can go a little bit further and say that we're using √2 sigma plus a little bit more. So I'm going to use that to change the inequality to a strict inequality. So this thing, strictly speaking, is less than or equal to, well, maybe you could write variance over √2 sigma plus epsilon squared. But the point is that whatever it is strictly less than 1/2. Because √2 sigma would give you 1/√2 root 2 squared, 1/2, and the plus epsilon makes it a strict inequality. And now we're just going to rearrange this left-hand side a little bit to contradict this property of the median. So removing the absolute values, we still have this inequality because we are taking a smaller set of outcomes on the left-hand side, so the probability can only get smaller. We're taking a smaller set of outcomes because the absolute value makes this a double-sided inequality, and removing the absolute value makes it a single-sided inequality. So we basically got rid of that one side that we were dealing with before. And now we can just rearrange this inequality. This is equal to the probability that x is greater than or equal to mu plus root 2 sigma plus epsilon. And this is what we said is m. So we get the probability that x is greater than or equal to m is strictly less than 1/2. And as we said, that contradicts the fact that the probability x greater than or equal to m, as we said up here, is greater than or equal to 1/2. So that is a contradiction, and that completes the proof. So again, just to recap what we were saying here, Chebyshev's inequality tells us some kind of concrete interpretation of how the variance or the standard deviation controls how wide the distribution can be. And as a nice little application, it allows us to show that the mean and the median of a distribution cannot be too far apart, measured concretely by root 2 standard deviations.